Okay, so let's look at example 4.2, and here we asked if the normal boiling point of hexane is 69 degrees Celsius. We need to estimate its enthalpy of vaporization and also the vapor pressure at two other temperatures. Right, so the normal boiling point or whatever, so when we are given the normal boiling point, it always of course refers to the boiling point at 1 atmosphere. I can write that better. So the boiling point at 1 atmosphere, or of course that is 101.325 kilopascals kPa. Whichever system you're working with. So in other words, that is the normal boiling point. So in other words, that is the pressure at which, so at that pressure, the boiling point of hexane is that temperature. Okay, that's the vapor pressure of hexane for that temperature. Okay, then we're asked to estimate its enthalpy of vaporization. So for A, we're actually going to use Trouton's rule. And if you recall Trouton's rule, have to go back a little while, then it said that the enthalpy of vaporization divided by the boiling temperature is approximately equal to 85 joule per Kelvin per mole. Right, is the boiling temperature. So in other words, the enthalpy of vaporization is then approximately equal to TB times 85. Just not going to write out the unit, which is equal to, in this case, so what is the normal boiling point for hexane? We're given it as 69.0, but of course that's in degrees Celsius. We just have to convert that to Kelvin, and that's times the 85. This is of course in Kelvin, and this is in joule per Kelvin per mole. So then we're just left with joule per mole, and the answer here is approximately, let me just quickly get my calculator. So 69 plus 273.15 times 85 is then 29,082.75. Of course that's joule per mole, which is then rounded off to 29 kilojoule per mole. And why only 29? Because 85 is a significant figures, significant number of figures, so that's 2 of them. So that gives us the enthalpy of vaporization. All right. So anyway, we're going to use this calculated value a bit later in the B section. So let's move on to that. Then we're asked to calculate the vapor pressure at 2 other temperatures. So in other words, we're given the normal boiling point, but then the vapor pressure of hexane at 2 other temperatures. In other words, what would need to be the pressure exerted on hexane liquid at 25 degrees Celsius and at 60 degrees Celsius for it to boil as well. Right, that's essentially what it is asking us. And for that we require, of course, we can use the Clausius-Caplayron equation in its integrated form. So we can start with ln of P2 over P1, and then with the enthalpy of vaporization divided by R, 1 over T1 minus 1 over T2. And then we just need to take the exponential on both sides. So we take e to the power this and e to the power everything there. So then we're left here on this side with P2 over P1 is equal to, so I'm just changing the notation to write out exponent. Then of course becomes VAP over R 1 over T1 minus 1 over T2. And then we can just multiply the P1 to this side. So then P2 remains on this side, and then P1 sneaks on in here. Okay, so there we have our expression to calculate given, so in other words, the new vapor pressure. So the new vapor pressure is this one, what we are calculating at this temperature. So that is at the new temperature. So just remember that those two need to go together. I mean, the subscripts imply that, but you just need to always keep that together. Okay, and then basically we just need to plug it in. So we just need to recall so P1 is of course the normal boiling point or the normal vapor pressure. So that is 1 point. I'm going to use just pascals, remember, because we need to work in pascals, not kilopascals. So times 10 to the power 5 Pascal, and then of course T1 is then going to be 69 plus 0.0 plus 273.15 Kelvin. Okay. Other things that we have, delta VAP H is equal to, what's that, 29082 stuff joule per mole. Right, that is the, yep. And yeah, I think that's everything that we need. So, but in this case, we first let T2 equal to 25 plus 273.15 Kelvin. Okay, so we first do the calculation for the 25 degrees Celsius. So if we plug in all those values, then therefore P1 is equal to 0.01325 times 10 to the power 5 pascals times the exponent of 2.90 and a bunch of stuff times 10 to the power 4 joule per mole, all divided by R, which is 8.3145 joule per Kelvin per mole, and this needs to be multiplied by 1 over 69 because it's the one that goes first. 273.15, this is of course in Kelvin, minus 1 over 25 plus 273.15 Kelvin. Close the exponent bracket, and if you plug this into your calculator, you should get answer, should get a value in the end of 22 kilopascals, which rounds off to 22 kilopascals. Okay, actually not 22 kilopascals, we need to include another significant figure there. So now I just wiped it out. Oh, goodness sake. 325 times 10 to the power 5. And then E. One over 69 plus 273.15 plus minus 1 over 25 plus 273.15. Okay, then you get a value of 22369.807, which then of course rounds off to 3 significant figures. My apologies for the little mistake earlier, which is then 22.4 kilopascals, because this is just Pascal. See, because of this one there at the front, it's just Pascal, as in 22.4 Pascal. And then if we let T1, T2 equal to, it's 60, right? 60 degrees Celsius, so 60 plus 273.15. Okay, so look, let's agree to not rewrite that entire thing. So we just basically exchange that 25 here, for 60, right? Everything else remains the same. So we then get the 25 just becomes 60. We then get 7652.70496 Pascal, which then rounds off to 76.8 kilopascal. Right. Which, if we compare that to the normal boiling points, let's compare that. So in other words, at the lower temperature, we have, so the higher the temperature goes, the more pressure we require. It's an interesting relationship. It actually makes sense because it is a linear relationship, sort of linear, because the logarithm should do that as expected, and it should also increase. So yeah, it's just a short calculation. The main thing there is just to rewrite the equation in the way that you require it. Of course, getting what you need as the coefficient, or as what you required. So of course, we can ask you anything, to calculate the enthalpy of the vaporization, the temperature, the pressure, anything really. But you'll always be given a set of the coefficients, and then you'll be required to get one of the other unknowns. Okay, and then there's a lot of little calculation steps that might go wrong, but it shouldn't be too difficult. Okay.